Right, hello, and this video is going to be an explanation of fuel cells, what it is, how it works, and what are some differences between a fuel cell and the normal galvanic cell. So we're going to look at 9A, C, and D. I just want to start by going back to this diagram, which I think I've shown you at least twice before. And this is just how energy is transformed in a coal-fired power station, which is used to produce electricity from fossil fuels. And we talk about some of the problems with this particular method of producing electricity. And the one that I wanted to point out once again is just how inefficient it is, especially because of step 3 here, because you're turning a turbine using steam that is generated from the heat that comes from the combustion of fuel. So it is highly inefficient. And this table also highlights that problem even further. The process of going from thermal to mechanical energy is only about 45% efficient. The step after that, mechanical to electrical, is quite efficient, but overall the process is not very efficient because of this steam turbine. And one more issue with this method is that you have multiple energy transformations. And regardless of how effective or ineffective each step is, the more energy transformations that you have, the more energy will be lost in the form of heat. So having more energy transformations in itself is already an issue without having a step that is highly inefficient. And if you compare that to the energy transformation in a galvanic cell or batteries, there's only one single energy transformation, and that is from chemical energy to electrical energy, which is the same outcome that you want from a coal-fired power station. And this one's a lot more efficient because there's only one energy transformation. It's between 60 and 90%. So the question that I posed a few weeks ago when we started the topic of redox is, how can we apply this technology to produce electricity for general use? We obviously have already been applying this technology in the form of batteries, but can we, shall we say, make a giant battery that can actually supply electricity for the general public? And that is the purpose of this particular lesson, which, should I sit here? Can we apply this principle for the mass production of electricity? And let's just actually talk about the general features of a galvanic cell. So generally you have a sealed container. You just think about a common battery. You start with a fixed amount of reactants in the cell, and then you seal it. If the cell runs out of reactants, you either have to recharge it or you have to throw it away and buy a new battery. Which is a second point, you can only reuse the battery if you can recharge it. And generally we use metals as reactants for a galvanic cell. Do I have another point? No, that's it. And if you compare that to mass production of electricity, if you want to build a cell that's going to produce electricity all the time, it's not very efficient to have a sealed container and then you have to recharge the battery, or you have to, well, you probably definitely want it to be at least rechargeable. But it's actually probably possible if you could just make a cell that, instead of having a sealed container, is open, in the sense that when reactants run out, you can add more reactants in. It's also very important. This point, the second point, is probably more important than the first. That you, instead of using metals such as copper or zinc as the reactants, you probably need to be able to use something that's a little bit more abundant and renewable, because metals are not actually renewable. You want something that's more abundant, carbon-based preferably, because we can make carbon-based fuels from, for example, photosynthesis. So if you can come up with a battery that would use a carbon-based fuel, or something that we can produce over time, and a battery that is open, in the sense that you can add more reactants in if you want, then that would be a little bit more convenient for mass production of electricity. All right, just one more before we actually get to the point. If we talk about galvanic cells, you can divide them into three categories: primary and secondary cells, which we will talk about later. But the main difference between, so primary and secondary cells are your normal batteries, whereas primary cells just say an AA battery that cannot be recharged, and secondary cells would be a rechargeable battery. Fuel cells would be a third category if you consider it to be a galvanic cells. Um, it does have it does convert chemical energy to electrical energy, so it does fit the general definition of galvanic cells. But instead of being sealed and have metals as reactants, as you generally have for primary and secondary cells, it has a constant supply of reactants. Tend to use non-metal as reactants. Okay, so I'm going to talk about what a fuel cell is. I'm just going to very quickly read through this, and if you need to write anything down, you can definitely just pause the video. So the definition of a fuel cell is a type of galvanic cell, first of all, and it uses chemical energy. So the fuels can be hydrogen or other fuels to generate electricity. So I guess if you just look at the name, it's quite self-explanatory. So uses a fuel. Generally, you either have hydrogen or carbon-based fuel, and it's a cell. So it's a type of galvanic cell in the sense that it converts chemical energy to electrical energy. So fuel and a type of galvanic cell, which is what I wrote here. It's a type of galvanic cell that does not run down or need recharging, and the reactants are not stored in the cell but must continuously be supplied from an external source. So that's, I guess, those are the three general features of a fuel cell. Yes, and it generally produces, in terms of efficiency, because there's only one energy transformation from chemical to electrical, is generally quite efficient, especially when you compare it to, say, thermal power stations or coal-fired power stations. And you can use it for vehicles, buildings, or even cities, depending on the design of the cell. The one I have here is for an electric bicycle. So there are a variety of different types of fuel cells out there. All right, this is just a very basic schematic diagram of what it may look like. This is not the one that you ever have to draw. And if I look at it now, I really feel like I should do it again. But anyway, I'm just going to stick with it. So essentially what you have is a container. I just want to draw it in 3D for once, just for you to have a sense of what it actually looks like. So let's say you start with a container, and as we mentioned, well, as I have mentioned at least twice in the past 2 minutes, the reactants in a fuel cell are not stored in the cell but must be continuously supplied. So there must be some ways for the reactants to be supplied into the cell. So let's just say you have some openings here allowing for reactants to come in if they have to. And the way that a fuel cell works is the oxidizing agent is almost always oxygen gas, which you technically don't even have to supply. You just need to make it open in the sense that it can use oxygen gas in the air. And the reducing agent is going to be the fuel. Could be hydrogen fuel, could be some other types of fuel. And because this is still a galvanic cell, it still needs to obey some of the principles of a galvanic cell. And the most important one is that if you want to generate a flow of electrons so that it is electricity, you need to separate the oxidizing and reducing agent. So you can't just have the oxidizing and reducing agent mixing in this one container. That's not going to give you any electricity at all. Energy would just be released in the form of heat. So what I need is a separation. So I'm going to have a barrier between the oxidizing and reducing agents. And in this case, my barriers would be the cathode and the anode, which generally are made of metals, could be some other materials. The electrodes are very, very interesting in a fuel cell. But let's say, so you start with oxidizing reducing agents. They are separated from direct contact by the electrodes. And what is going to go in the middle here would be the electrolyte. So hopefully you can see already that there is no salt bridge, because you don't actually have two separate containers. If you have a giant box and then there is a barrier here, there's a barrier here. The electrolytes come in, so I probably need to have a wire of some sort to connect the cathode and the anode, so actually have flow of electrons. You can definitely see that I've given up on drawing the wire properly at this point when I made the animation. But there is no salt bridge, so but there has to still be an internal circuit. So we're going to talk about how electrons actually flow through this cell. Do I write anything else? Yep, so 2 compartments, you can say 3 compartments, I can't count. Oxygen gas, the cathode, field, the anode, and then electrolyte in the middle. All right, so that is the 3D drawing, if you will, of the cell. From now on, we're just going to look at it from a 2D perspective. We'll probably only draw this part of the cell. So I'm going to convert the I think I'm going to talk about this in a little bit. So I'm just going to go from 3D to 2D, and then I show you I'll explain the electrode and the electrolyte. So let's just use an example. So instead of 3 now this is in 2D. So you still have the 3 compartments, the 2 electrodes connected by a wire. Oxidizing agent is going to come in here, and reducing agent is going to be on the other side. So the example that we're going to use will be acidic hydrogen fuel cells. Hydrogen is the fuel, and if it's acidic, that is the condition of the electrolyte. So you have acidic electrolyte, hydrogen fuel in a fuel cell. All right, so hydrogen gas is on one side and oxygen gas is on the other side. Because it is a acidic fuel cell, the electrolyte must be acidic. So I'm just represent that acidic nature of the electrolyte using hydrogen ions here in the middle. Okay, so what actually happens is the first interesting things is, if you can see, if these 2 electrodes are complete solid and allow nothing to come through, then it's actually very, very inconvenient, because you can't really have transfer of electrons if it's just a barrier. So the electrodes are quite special. They're not just a solid barriers. The first thing about them is that they are porous. Please spell this word correctly in future assessments, which means that they allowed the reactants to go through them, and the reactant can go through them to move to this edge, which is the electrolyte interface. So for example, the hydrogen gas can move through the porous electrode and get to this interface. And the same can be done for the cathode. So the anode and the cathode allow the oxidizing and reducing agents to move through the electrodes into this electrolyte interface. All right, so what happened is the reducing agent here, which is hydrogen, is going to donate some electrons and becomes H2 plus. This is the oxidation half equation. So we have one more, donate some electrons and becomes H2 plus. Obviously, as this happened, the opposite process is supposed to happen as well at the same time. I'm just slowing it down so you know what goes where a little bit more easily. So let's start again. Let's say you start with the reducing agent. The reducing agent will donate some electrons and become H plus ions, following the oxidation half equation. And at the same time, on the other side, oxygen gas would accept some electrons and be reduced into O2 minus ions. So that's the half equation on the other side. So you have already movement of electrons in the external circuit. Electrons go from the anode into the electrical wire and then exit the electrical wire going into the cathode. Okay. The last thing that we need to talk about is the movement of the electrolytes or the ions. So the electrodes are porous and allow the oxidizing and reducing agent to go through, and then they will get to this electrolyte interface. But in order to achieve separations of the oxidizing and reducing agents, it's very important that the hydrogen gas and the oxygen gas cannot mix. So you can see here that the hydrogen gas and oxygen gas actually just stay at the electrolyte interface, and they can't actually go through the electrolyte and mix with each other, because that would defeat the purpose of a battery, and you would just have energy being released as heat. So even though the electrodes allow the oxidizing and reducing agent to go through, the electrolytes will prevent that. The electrolyte will not allow any gas to go through. The only thing that can move through this electrolyte is ions, or are ions. So hydrogen gas are produced on this side and consumed on the other side. And the reason why it is consumed on the other side, so you obviously can see in this case, oxide ions are produced, and they will combine with the H plus ions because opposite attract and produce H2O. And because hydrogen ions are produced on this side and consumed while they produce on the anode and consume on the cathode, hydrogen ions must move from the anode to the cathode. Another way to remember it is cations. In this case, the electrolyte ions is cations, will move towards the cathode. Now the water is actually the product, and because the electrolyte is a solution, water can move through it, and it's just going to be extracted from the electrolyte. So the second equation here, which is actually not a half equation, it actually shows the combination of oxide ions and H plus ions turning into water, which would then be removed from the electrolyte. This is a fantastic device in that it produces water as the product, which it's very useful, and it's not carbon dioxide. All right, what tends to happen in year 12 is you allowed it to just combine the two half equations together to get O2 plus 4H plus and 4 electrons going to 2H2O. But keep in mind that this is actually the combination of the actual reduction process and the combinations of H plus and oxide ions. So what I wrote here, the electrolyte is impermeable to gases and electrons, but allows hydrogen ion to go through. So now you have your flow of ions, which is the internal circuit from the anode to the cathode. All right, this is another summary of this, which is the very first type of fuel cell that you need to know, which is acidic hydrogen fuel cell. If I add the two half equations together, I get this overall equation, which is just H2 plus O2 going to H2O. Electrolyte hydrogen go to the cathode. And what I want to point out with the overall equation of not just this fuel cell, but any fuel cell that you're going to encounter is that the overall equation of a fuel cell is identical to the equation for the complete combustion of the fuel in oxygen. If you just look at the equation, if I just cover everything else and give you the equation, it looks identical to a complete combustion. And that is a very, very useful thing to remember, because every time you see a fuel cell, for example, I say hydrogen fuel cell or methanol fuel cell, you should always be able to write the overall equation for that fuel cell, because it looks identical to a combustion equation, a complete combustion equation. Obviously not in oxygen. However, it's important to keep in mind that no combustion actually takes place, because there's no direct contact between the oxidizing and reducing agents. Instead, they are separated, so energy, instead of being released in the form of heat, is released in the form of electricity. Now, because there is no actual combustion, this reaction actually happened very, very slowly, because if you think about it, things don't just combust spontaneously unless you provide a spark. You don't have a combustion here. The reactants are not even in direct contact with each other. So if you don't have a spark as well, it's actually a very, very slow reaction. It's a spontaneous reaction, but it's incredibly slow. So because it is very slow, you generally need to have a catalyst to speed up the reaction, which is basically the function of a catalyst. And most commonly, a catalyst is going to be embedded in the electrodes. So the electrode not only is porous, it's also catalytical, or it has catalyst embedded to it. The two common catalysts used would be platinum and nickel. Okay, so I think this is more on speeding up the reaction. So if you want to speed the reaction up, you could increase the temperature. That's another way to increase reaction rate. It's not very convenient though, because you may speed up other side reactions. You may require some specific materials that could withstand the high temperature. If you're thinking about using fuel cells in a car, you don't want the temperature to be very high, because it's very hard to manage and it's quite unsafe. Using a catalyst is a much better method to speed up a reaction, because it tends to be quite specific. A catalyst can only speed up certain reactions, so there's a lower chance that you're going to speed up any unwanted reaction. It also allows you to operate the cell at a lower temperature. Now, the thing with catalysts, and we're going to talk about catalysts a little bit more later on when we talk about reaction rate, but this is one of the issue with fuel cells actually. Platinum is the best catalyst to date. It's very, very effective. It allows the cell to be operated at low temperature, so less than 100 Celsius degree, and still achieves the desired electrical output, because you can't just produce a little bit of electricity. You need to produce a lot for this to make sense. However, platinum is a very, very expensive catalyst, and it is also highly sensitive to impurities. So if you have some impurities in the fuel, if the fuel is not properly distilled, it could potentially poison the catalyst, which is the verb that we use when a catalyst doesn't work anymore, and it is very difficult to fix that problem. Other catalysts, so if you don't use platinum, you could use some nickel-based catalyst. However, it's not as effective as platinum, which means that you need a higher temperature to compensate for that, and that may mean that it's not suitable to use on portable devices such as a car. So you may use it to produce electricity for household, but still, higher operating temperature generally means that it may be costly to maintain. You need specific materials, um, all of that. So that's the issue with fuel cells. The best catalyst is too expensive. The cheaper ones require higher temperature, which makes it quite inconvenient. All right, but if I just go back to this slide, which I think I'm going to move to the end and just summarize the properties of everything. Obviously, yeah. So the electrodes, in order for the cell to function, obviously the first property of the electrode is the property of any electrode. It needs to conduct electricity, so electron transfer can actually occur. Um, in this case, the electrodes are always inert because the oxidizing agent is always oxygen gas, and the reducing agent is the fuel. So the electrodes would never actually participate in the reaction. I'm sure there are exceptions somewhere, but in generally it doesn't. But for a fuel cell, this is specific for fuel cell, the electrode has to also be porous to allow gases to go through, and it also need to be catalytical to speed up the reaction. As I just mentioned, platinum or nickel is going to be embedded in the surface of the electrode. And lastly, it must have a high surface area. So not only is it catalytical, it also needs to, so you have the catalyst embedded throughout the electrode. You also need high surface area, which I think also is why it's porous. The higher surface area of the electrode is, the faster the reaction is going to be, and the size of the current is going to increase as well. Now with the electrolyte, and we only gone through acidic hydrogen fuel cell, the electrolyte, well, general function is it's a material that conducts electricity via flow of ions. I was going to say electrons. In this case, it's going to carry ions from one electrode to the other to complete the internal circuit. In the case of an acidic solution, because the ion in the electrolyte is H+, which is a cation, the cation is going to flow through the cathodes, but you can have some other examples as well. For example, obviously you can have an alkali electrolyte, but you can also have liquids such as phosphoric acid, or in extreme cases, molten carbonate salts or permeable membrane. So there are solid ceramics. So they have multiple types of electrolyte. But it's always important to remember that cations would go to the cathode and anions would go to the anode. I think that's it for general features of a fuel cell. No, I do not want to keep that.